Well, good afternoon, everyone. My name is Guilhem ICR. I'm working currently as a professor assistant at the INSA Lyon in France. And today I'm going to tell you about the work of the PhD thesis of Matthias Nebui, who was working with us for 3 years. Now he's about to defend his thesis on December 17th. And it's all about multi-block copolymers and mainly how we can model shear-induced crystallization that is occurring in this kind of system. So the system here that I will speak about today is a multi-block copolymer, which is made of soft segments and hard segments. The idea is the following, is that you start from a polymer melt, that you decrease the temperature, and the hard segment, they will associate, they will form ribbon-like crystallites typically. Of course, what is nice about those materials is that if you increase the temperature back, then the system will melt, so that you will dissociate the hard segments, and you will get a material which has the structure of a liquid, which is not the case for vulcanized elastomers, for example, in which you cannot make liquid the material, and that's a big issue actually for recycling. And so here, what is cool about TPE, so thermoplastic elastomers, is that you can use them for all the melt processing techniques that we have, for example, extrusion, injection, hot pressing, and that make those materials very good candidates for many different applications in the industry. And in particular, you can find them to insulate electric wires in the transport industry, so they go into the bitumen. Many different consumer goods. Also, what is interesting for a few years is that some chemists start to work on biosourced R segment. So those molecules, they are at least partially biosourced, which is let's say a good sign for the future. And we can cite also the fact that the market of TPE is growing continuously and typically 5% per year, which is still very significant given the current conditions. So more particularly, the material that I will speak about today is a multi-block copolymer made of PBT for polybutylene terephthalate and PTHF, polytetrahydrofuran, which plays the role of the soft segments. It has melting point, which is close to 180 degrees. And so here the idea is to work in between the melting and the crystallization points so that we can try to apply some shear to promote the crystallization of the hard segments. So that's an example with SAO, so a small amplitude oscillation shear along the crystallization. So here we follow G prime and G double prime as a function of time. And what we see is that we start with a viscoelastic fluid with G double prime, which is bigger than G prime. And then little by little, we will have some crystallization. And so that in the end, we get a material which is more elastic than viscous. And typically, that's the crystallized elastomer with a modulus, which is close to, in this case, 1 megapascal at 140 degrees. And it will reach something like maybe 5 or 10 megapascal at room temperature. So this was for linear rheology following the kinetics of crystallization. But of course, what we're interested in here is to apply some steady shear to the material. And we can do this by using this famous cone partition plate. So that's typically what it looks like. And you have all the details in the paper by Salvatore Costanzo and co-workers published 2 years ago. So here we apply a steady shear and we see what happened in terms of crystallization kinetics. That's the green line, so it's with steady shear, in comparison with the blue line here, which is the SAO's data that we transform assuming the validity of the Kotzmer's rule. And here what we see, which is quite clear, is that crystallization is happening earlier when we shear all the time in the same direction. And so this is a clue that we are promoting somehow the crystallization by applying some nonlinear rheology here. So what is particularly interesting to follow is the onset of the crystallization here. So we see that we have clear shift at shorter time when we apply steady shear. And eventually at longer times, the material, because it becomes solid after the crystallization, then it will break literally in the rheometer, and then we get kind of powder of TPE. So we are completely sure that the material is broken. And so I will not show you, of course, the data after the first cracks appearing in the materials, although some of them might be of interest. What is particularly interesting then, of course, is to change the shear rate. And here, what one may have expected is that by increasing the shear rate, then you make the crystallization earlier. And that's pretty much the case. That's exactly what we see here. So we pass from a kind of slow crystallization in the case of sows, so a quiescent crystallization, the turtle. And when we increase the shear rate in a steady shear manner, then we have the rabbit-like crystallization. So this was expected once we discovered the green line at the beginning. And what is very interesting here is that if you plot this data, stress as a function of strain and not stress as a function of time, what you see is that you have a kind of collapse of all the onset time. And this is telling you literally that you have strain-induced crystallization, because it is for a certain value of the strain that the material will start to crystallize in this way. So how can we explain the strain-induced crystallization? We have the answer in this little scheme from the book of Michael Rubinstein and Ralph Colby here. And so they are telling us that if we apply a shear rate which is larger than the reciprocal relaxation time of the polymer, then this molecule has no other choice but to align in the direction of the flow. And by aligning, then it will promote a nucleation. And so here, if we have a look at the linear data to extract this terminal relaxation time, which is traditionally taken as the crossover between G prime and G double prime in amorphous polymers, then we see that this time corresponds more or less to 5×10⁻⁴ second at 140 degrees, which is the temperature at which we work for our experiments. And so if we transform this in terms of shear rate, then we understand that we need to apply a shear rate which is higher than 2000 reciprocal second, which is of course not really feasible with our rheometer. Typically we can reach 100 or 200 eventually, not more than this. This is a big question for us, because we do see strain-induced crystallization, as I showed you before, but apparently we don't go fast enough. So how is it possible? If we look more carefully at the TPE data, and here it's a frequency sweep which is performed above the melting point at 200 degrees. And if we keep on measuring at very low moduli, so very low frequency and high temperature, what we see is that we have secondary plateau which is appearing. And so this is telling us that our TPE is not behaving as Maxwellian fluid. So it's not behaving as a usual amorphous polymer, but rather that we still have some phase separation in the polymer. And of course, this might be discussed. You may not agree from the frequency sweep that this is obvious. And so we had to fight actually with some reviewers, and the answer was brought by a creep experiment. So when you do creep experiment here, still above the melting point, so which is close to 180 or something. So here we are completely sure the material is purely amorphous, but still we see that around 100 or 1000 seconds we have plateau. And this plateau in compliance is telling you that you should have also a plateau at low frequency here for G prime and eventually G double prime. So when you do the compliance inversion and you match it with your frequency sweep, you have beautiful match, and you clearly see that in fact you do have some elasticity remaining in the fluid at very long time. And so this is telling you that you should consider also those times for the chain alignment, and not only the crossover of G prime and G double prime. And so in the end, the strain-induced crystallization idea, which is telling us that we need alignment of the chain, is compatible with this material. And this is because we still have phase separation in the melt. So this is a strong statement. that makes shear-induced crystallization possible here, we believe. So the idea is summarized in this little scheme is that because we do have a phase separation, then when we will align the chain, so because those nodes exist, then they will allow somehow the alignment of the chain. That's the story. So then to model the stress along this steady shear experiment, of course, one may use the Dooyeweerd model, which is based on two different ingredients, the memory function, and you see that in this memory function, you have the disentanglement time of the polymer, usually, which correspond to this crossover at G' and G double prime. And you also have the nonlinear spring that you consider. And so in the case of Dooyeweerd, they have particular shape. Other nonlinear springs exist, but I will show you that in our case, the Dooyeweerd nonlinear springs works pretty well. So based on the linear rheology, then we can fit this data with a multi-Maxwell fit as it is done usually. And so the sum of different Dooyeweerd terms. So one term takes in consideration a couple, modulus, and relaxation time. If you sum all of them, then you get the full response of your material. And here in the graph on the bottom right corner, what you have is the black line is actually the Dooyeweerd model. And you see that it works pretty well with our rheological data. While the dashed red line is the linear envelope. And you see that, as you might expect it, there is a significant shear thinning here. And so this is supporting the idea that we have chain alignment, because by aligning the chain, then we will reduce the number of entanglements, and therefore the viscosity will decrease in the nonlinear conditions. So at short times, it seems that the Dooyeweerd model is working pretty well, actually, almost perfectly. On the contrary, at long time, of course, the Dooyeweerd model does not in consideration the fact that your relaxation spectrum is moving with time, and in particular, this tau d is not a function of time, so you do not expect the Dooyeweerd models being able to model this kind of data. So the idea for us was to imagine a framework in which we could play with this relaxation time as a function of experimental time. And the idea was to consider our polymer, which is here red and blue, as a supramolecular polymer in which the stickers, they are nothing else than the hard segments. So if we do this, then we may use different models that have been built somehow for supramolecular polymers, and in particular the one by Gonzalez, published in 1988, 3 years before the seminal paper of Leibler, Rubinstein, and Colby about sticky reptation. The main difference between the two models is that here Gonzalez, actually it's a bit more simple, a bit simpler, is that the relaxation time he considers, which is called tau F for effective relaxation time, is simply the ratio between the reptation time at the beginning of the experiment divided by the probability that no sticker is active in the chain. So if you have one sticker which is active, then the reptation is forbidden. And so the main difference with the sticky reptation model is that in this case, the model does not allow the dissociation. So once you are associated, then it's the end, basically. While the sticky reptation model is more is considering kind of dynamical mechanism, which is more physical for supramolecular polymers, but not necessarily in our case, because in our case we have crystallization of the hard segment, which means that the objects are continuously growing. And if they are continuously growing, it means that the stickers, they have to stay stuck all together. So in average, they do not have the right to dissociate. Or if they do, they associate faster than what we dissociate. So in the end, we believed that the Gonzalez model was satisfyingly describing our data. So here quickly, P naught is the probability that no sticker is active in the chain. P is the probability for a sticker to be associated. And so in our case, it will be the probability for the hard segment to be to belong to a crystallite. And F is the number of sticker per chain. So in our case, it's the number of hard segments which are crystallizable in quiescent condition, which is roughly 30% of the chain. So we have something like 2 stickers per chain in the end. So we have this parallel between the association and the crystallization. So the probability of association has to be related with x of t, which is the crystalline content as a function of time. And we know that this is well described by the Avrami equation. And actually, we evidenced this, the fact that the Avrami was working well in our case in the paper we published last year. And so here we can have the K, which is somehow the speed of crystallization, and N, which is the growth mode, which is telling you the shape of the crystals that are forming in the material. And so when we consider this probability of association and the Gonzalez model, then we can have a new expression for our relaxation time, which is called in this case tau, and is a function of the experimental time. And therefore, it becomes a function of the Avrami parameters, here K prime and N. Also, we need a connection with the shear rate. So here it's given by the ideas of Eder and Yanisich-Kriegel. And it works also pretty well in our case. So the induction time scales with the shear rate to the power of -1. So 1 over the shear rate, inversely proportional to the shear rate. So when we have this, actually we have a new little equation, which is K prime moving in a linear way with the shear rate. And so we can combine the two blue equations that we have in front of you. So we can re-express the relaxation time here as a function of the initial rotation time, which was the crossover, let's say, between G prime and G double prime, and some parameters which comes from the Avrami model that we investigated last year. So we can reinsert our relaxation time in the memory function, and now the memory function is depending on the experimental time. So in the big equation of the Dödler model, then we have this integral between t prime and t for the memory function. But apart from this, the model is conserved. And what is interesting, of course, is to see that it works pretty well. So here, what is important to say is that the Avrami parameters, they are fixed for all the curves. They do not depend on the shear rate, of course, otherwise it would be too easy. And so here what we find when we fit the data with our modified Dödler model, alpha and beta, so they have this particular value of 1.3 10 to the -3 7 minus n, and n is 1.3. Here quickly a comment is that n 1.3 means that we have elongated objects. Typically in the Avrami theory or the Avrami model, n is more or less the dimensions for the growth of the crystals. So when n is close to 1, it means that you have something like rod-like crystallization or a ribbon when it's slightly bigger than 1. And of course, that's exactly what we have in the material, so we were very happy. And what is interesting also is to compare the fit parameters that we used here for the nonlinear data to quiescent crystallization. And they are very close, so n is exactly the same, and alpha and beta gives you a good approximation of your K. So it seems that we managed to capture the global picture for this material. To validate those results and this kind of closure, then what we could do is to interrupt the startup flow at different time, T1 in this case, along the crystallization, and see what does the relaxation look like. And if, in principle, if we can extract the relaxation time as a function of T1, then we know how it evolves with the experimental time. Therefore, we can validate or not what we did in the previous slides. So when we do this, we can fit then the relaxation with some models, which are detailed in the paper. I will give you the reference at the very end. And so by plotting here the relaxation time as a function of the experimental time, again, we see that we have this beautiful exponential trend with the parameters which are extremely close, again, to the fit parameters we used to model our strain-induced crystallization. So here we find, again, alpha and beta 1.3 10 to the -3, so -n, and n 1.3. So here it's not really fit, it's like simulation, so it's very close in any case, and it's discussed in depth in the paper. Perspective for this work is to use coarse-grained molecular dynamics simulations in startup flow to see whether we really have chain alignment and quantify it, having the position of all the beads in real time, or at least in linear James time. And so this has been done thanks to a first simulation box that we published this year in Macromolecule. So it's mainly the work of Matthias Nebui and the team at INSA. And so here we beautifully see that we have chain alignment with the flow direction. And on the right, what you have is the shear-induced crystallization. So the promotion of the phase separation when we apply some steady shear. What is interesting on top of this, it's not only qualitative simulation, but we can really do some quantitative analysis. And in particular here, we can observe how the stress tensor here, QXY, which was the F1 in my previous equation in the diagram model, is moving with the strain. And we find that the famous results that has been highlighted by Doyen Edwards is the stress overshoot, which is at gamma equal 2. And that's exactly what we find here when we do the analysis of our simulation boxes. And finally, and this is my last slide, then another perspective is concerns the laws. Here the question was, okay, we know that we enhance the crystallization with a started flow. What about oscillatory shear? What about an oscillatory flow? And so here we did exactly the same kind of experiment, but in Laos. And we've been able to evidence that we had the same effect by increasing either the amplitude of the strain or the frequency of the solicitation. And of course, both parameters are very much related with the shear rate. And actually they are proportional to the shear rate. So when you increase either the amplitude or the frequency, then you are increasing the maximal shear rate. So it makes completely sense that we find also in the case of Laos, an acceleration of the crystallization, of this strain-induced crystallization. This has been submitted to Journal of Rheology, and we hope that it will be published soon. So with this, I'm done. I just want to acknowledge my co-workers, in particular Matthias Nebui, who did a fantastic job in our group for 3 years. We will miss him very much, actually. So he defends his thesis on December 17th. Also, André de Almeida, who was a postdoc working with me when I arrived in the group. Claudio Fusco, Julien Mortomas, who are my colleagues at INSA. And they were mainly involved in the work concerning the simulations. And Laurent Chazot also was the supervisor of Matthias. I'd like to thank also the French Ministry of Research for the funding, DSM for the material, and the EUSMI, which is the European Soft Matter Infrastructure, for funding the experiment that we perform in Crete in the laboratory of my ex-boss, Dimitris Vlasopoulos. I thank you, Dimitris, very much also for your kind help with those experiments. And Daniele Parisi also was working with us on the machine and was helping us with the experiments. As I said before, then you can find all the details, all the details on the experiments and the materials in this paper that you have at the bottom of the slide. I thank you very much for your attention. I hope you enjoyed this webinar, and I think that now I'm ready to reply to your questions. Thank you.